Thank you. Good morning, everyone. So quick show of hands, how many of you have actually tried tracing in your production applications? Okay, that's quite a few. So never mind. We'll go through the basics of it first, and then we'll come to like what are the problems we are facing, or what are the pitfalls, I would say, that we have in the say in most of the implementations, and how we have tried to address it using a layer over the distributed tracing, the generic way, and how specifically we have improved and got a accuracy of say more than 80% of the things that we are not getting earlier by using the generic or say the randomized sampling. We'll get to the details in a bit. So yeah, first of all, introduction to distributed tracing. So as you all know that with the advent of say distributed systems and like large-scale microservice architecture, we have multiple like tens of thousands of services that have come in, and they have interdependencies and thousands or millions of requests per second coming to a particular service. Let it be a front-facing service or a critical component of the whole service mesh. We have been getting like multiple requests that needs to be served at a neck-breaking speed. So how do we know that and how do we ensure that our application stays on top of this and is available like all of the time, like if not say 5 nines, at least 4 nines or 2 nines, whatever is the SLA that we set. To ensure that we have multiple mechanisms to do that, and those comes under the observability and monitoring and alerting bucket. For example, like if I say we use matrix and logs, which would be a great step in say allowing our services to be in allowing our services to not go down and to see what are the possible things that are coming and which might fail our services. That is something which still lags and which we want to know, that how do we know that end-to-end things of all the services, like where did my request originate and where did it end, and between this, if it dropped somewhere or it got stuck somewhere, how do I know that where it got stuck and what was the root cause of it, because we are jumping multiple requests here. Here comes distributed tracing, where it captures each and every request that goes on from the start point till the end and all the things in between. So yeah, let's go by definition. So distributed tracing is a method to monitor and profile applications, particularly in a microservice-based architecture. As I mentioned, the goal is to provide a comprehensive view of the behavior of such applications, including performance of each individual component that interacts in this whole ecosystem. By this, we come to know of the bottlenecks, first of all. Then we get to know that how can we improve the performance of a particular service. If we continuously know that, okay, my request, say 60% or 70% of the time comes and fails in that particular component, which might be somewhere in the middle, lying in from their start to the end point. We definitely know that something is going wrong here. We need to come back and fix it. So basically, yeah, we collect all this information and come out and say that, okay, here is my problem, and here is like how I identified it using the traces. So some keywords that we'll be focusing mainly on is span, traces, and sampling rate. The whole talk would be based on the sampling rate and how we have figured out a way to adjust it. So yeah, before that, how distributed tracing works. Here's a brief diagram of, I think it was shared earlier as well. So this is a generic diagram of how the distributed tracing is. We, as per the terminologies, we have something known as traces, which is the backbone of it. So each request is assigned a unique identity, which is known as a trace ID, and is basically identification of all the traces that goes in from the beginning to the end. Then we have spans, which represent individual operations within a trace and would provide details of multiple contexts or tags, that is the duration, name, we can add multiple custom tags as well, like the originating host name or the status code that we want to record for it, all those. So as the request flows through the various services, additional information is added to the traces as tags. So in a distributed system, distributed tracing system, this all is aggregated into one, and which helps us in basically visualizing the whole thing at one place and taking business decisions out of it. So as I mentioned, we'll be discussing also the current landscape of how things are currently and how there's an attempt to improve it. So with the Dapper-based tracing implementation such as Zipkin and Jaeger, and by default, it employs a random-based sampling, which is like something close to 1 to 5%, because more than that obviously we can do it, we can do up to 100%, but it comes with the cost of increased CPU and storage requirement for all the traces. So that's why out of say 100 traces, we are able to set, say whatever is the limit, like 1 to 5% of the traces. The issue with this is that, suppose we are doing it with a threshold of 5%, all the other 95% of the traces are missed. And you can figure out like what is the possibility of not having these traces when there is a production issue. So like I get an issue, or say pre-production issue, I get something is not working, I quickly go and check like, okay, I see the matrix, it shows me, okay, CPU is high, I see the log, it shows me some log traces, and then I go and see that, okay, where it has failed and which particular service. In that case, imagine this trace falling into that 95% of your sampling, which was not collected. I mean, I have the indications, but I don't have the full picture, and I don't have a help from traces. So that is the case which we are missing. And also, when I say that the 5% of the traces, there is also a possibility that the 5% traces need not necessarily capture the faulty traces or the traces that are of interest to us, that could essentially capture the production going down scenario. And most of them, by default, use head-based tracing, head-based sampling. So what is head-based sampling is that at the beginning of the trace itself, it decides that, okay, do I need to pick this trace or not? So by this, what happens is we essentially are restricting it to collect the trace of interest. By interest, I mean the trace which would point to our issues. As I mentioned, the storage and compute plays a bigger role when we increase this from 5 to say 10%, 20%. We require a higher storage for that. So sum it up, keeping a fixed or high rate of sampling requires more computation and storage requirement. Lowering the sampling rate, or say doing a randomized sampling, risks of losing out on the valuable traces. So the modified or the working solution, or the ongoing solution that we have is something that is earlier, before this statement, we had, in the initial days of this implementation, we had only tail-based sampling, where we decide at the end of the trace, based on certain features, that if this needs to be taken care or not. I mean, this needs to be considered for saving in our tracing storage or not. But now, we have found a bit of modifications and are using a combination of head and tail-based sampling. Why is that is, as I mentioned, only using head-based discards the trace from the first step itself, that if it does not fall in that 5% probability, it will be discarded. But using a combined approach helps us in capturing traces in such cases where there is, suppose, a new component or a new whole service that is deployed and we don't have traces for it. For that, we would definitely need to catch those traces and save it, rather than doing a tail-based sampling, which would again be a overhead, as in we do it after that. We already know that this is a new service oncoming, so might as well collect all the traces of it for a certain duration and then tune it according to the tail-based sampling over a period of time when we have a lot of data about the new service. So that's the filtering criteria that we use, the combined head and tail-based sampling. Now, sampling is as I mentioned, the adaptive sampler that we are using, that is pretty adaptive in nature and reacts based on the feature vectors that we have, that we take out from the traces that we collect. So feature vector that are generated, few of them that we are basing the trace collection on is the operation method that it is, the operation path that is from, say, service A is calling B to C, D, like that. Suppose, say, we have predicted that A goes through A, B, C, D, E, and there is, say, the service C is where it has failed. Then definitely over time, we have learned that it has gone through, say, A to E. Then we essentially sample that and give that weight according to the end destination of that particular trace. Then there is your service name that is going as a tag. Then you have the span. Then it comes to a span level. This is at the trace level. Then it comes to a span level where you have the span's host name. Then you have the status code that it is reporting and the other set of spans and the respective features. Now, how do we sample it? We use something known as a spatial distribution, that is as simple as the density-based scanning, where we assign certain clusters, and each cluster has a definite weight attached to it, and each cluster's features would be based on these feature vectors which I earlier mentioned, and it will have a certain weight on each of these features. So say a new span comes in, it needs now the adaptive samplers engine which is there. The main goal of that engine is to decide where it should lie on, like where that particular trace which cluster it should go on. Based on that, it adds the weight to it, and according to that weight, it is assigned to that particular cluster of that whole sample. So as I mentioned, each trace is assigned a particular weight, which is nothing but an inverse function of the occurrence of these feature vectors. Suppose, say, I have certain 200 OKs collected for a service. Now I want, say, non-200 OKs to be collected because 200 OKs might point to something that is already working fine. Now I want to know that, okay, what are the non-200 OKs that I want to collect on? So in short, the inverse weight function which I mentioned gives more weightage to the ones which are not collected, which status code is not collected, or say which service is not represented in the whole trace collected ecosystem. So yeah, basically this would be the whole overview of the architecture that we have for the system. We have the microservices where they generate the spans, that aggregates the spans, and then we have a trace cluster, which basically clusters all the traces based on the all the collections that we have. Then we have the adaptive sampler engine, basically which does the inverse weight function to assign weight to each of the each of the traces, and then based on this weight, decides on the threshold that if this trace needs to be stored or not. Yeah, that's the whole thing of it. And yeah, maybe you can add some questions.
Right, thank you.